So today we want to discuss a very fun topic, and it's the hydrogen atom. Okay. So it's one of the simplest systems that we have in our universe, and it's a fundamental building block, right? It's a fundamental building block of our universe, right? The initial state of the universe was nothing but a plasma of protons and electrons. And when it cooled down enough, they recombined into neutral hydrogen atom mostly, or molecules of hydrogen. And the universe suddenly became transformed from being an opaque place where light could not travel without getting scattered, and therefore you could not see anything. The universe became transparent. And that is the surface of last scattering that we now see its echo in the cosmic microwave background, the 2.7 degree microwave background. Okay. So the hydrogen atom is one of the fundamental building blocks for our universe. So it's also one of the few quantum mechanical systems or real life quantum mechanical system. Let's put real life. Quantum mechanical system, that is exactly solvable. I'm going to put more or less. Even there are subtleties that quantum mechanics is not able to handle very easily. So historically, the hydrogen atom was also a big success of the old quantum mechanics. By old, I mean the Schrödinger equation or Heisenberg equation, quantum mechanics. Okay, so the quantum mechanics that was discovered or initiated by Max Planck. Albert Einstein. There's a lot of other names, Niels Bohr, etc. And it was really the hydrogen atom model put forward. The first hydrogen atom model that was put forward was by Niels Bohr. Okay. Now that is called the Bohr atom. But the Bohr atom had some arbitrary assumptions, okay, ad hoc, I should say. Had some ad hoc assumptions. Although it was very successful, it had some ad hoc assumptions. Before we discuss the assumptions, do you know how it was successful? What is it that the Bohr atom was able to explain very successfully?
I don't think I know. I think it's something like spherical symmetry or the electron spinning around it, maybe?
No.
Okay.
Anyone else? Good try. It was very successful experimentally in explaining certain experiments.
I mean, I would share. That it's the model where most of it is empty space. So
Yeah, it's
isn't
most
that
empty space,
the
but
isn't
experimentally,
that what it
what
explains?
experiment? Yeah, what experiment does it successfully explain that?
Oh, it's the gold foil experiment, right?
Okay, that's actually good. That's not what I was thinking about, but that's actually good. Anyone else?
Sir, was it the model of the atom?
Was the first. Yeah, that's exactly what Rahul was saying, because the model of you're thinking of the Rutherford model of the atom, right?
Yeah.
Where Rutherford said that, oh, before Rutherford, there was this other model of atom which was more like the atom is it's like a pie with
Like the plum pudding model, I
yeah,
guess?
yeah. It's not the plum pudding model, but the Rutherford model was that. Okay, so the plum pudding model was something like, okay, we have some kind of cloud of, I think, negative charge or something, I forget, and in it, they're like these plums of positive charges or something like this. And then Rutherford did some scattering experiments, and what he did.
Wasn't it the other way around?
Yeah, it must have been the other way around. I think it's the positive charge and the negative charge being electrons, right? Yeah, sorry. I forget. I mean, the plum pudding model, I never engaged with it, let's just say. Okay. But you're right. And then Rutherford said, okay, he took a very thin foil of gold, so just a few atoms thick, and then he scattered some very high energy alpha particles, and what he found is that most of the alpha particles went just right through, and some had like little bit of bending, but not much. But once in a while, there would be an alpha particle who would just like ping go back, right? So Rutherford from there kind of said that, okay, the atom should basically be some very dense core of positive charges, and then surrounded by mostly empty space with the electrons, perhaps whizzing around in some fashion, right? Of course, this was a challenge for classical electrodynamics to solve, because for this to be a finite system, which it is, right? It's a bound system. The electrons will have to travel in non-rectilinear orbits, right? Not straight lines. That means that electrons would have to accelerate. And we know from classical mechanics that when electrons accelerate, they emit charges. So they emit electromagnetic radiation because they're charged particles. And therefore, if they emit electromagnetic radiation, they will lose their energy and then quickly fall into the nucleus. And therefore, the atom would not be a stable system. So what Bohr did is that he of course made some ad hoc assumptions which allowed those features to be implemented. But there was another set of experiments that Bohr's atomic model explained, which is if you take, say, a glass jar or something, and you have some kind of anode and cathode here and here, and suppose the voltage between them is very, very high. You put like a huge battery, and you fill up this glass jar with some hydrogen. If it's a neutral hydrogen, okay, or any other gas. It doesn't have to be hydrogen. It can be any other gas, but hydrogen being the chemically the simplest molecule, it was easier for Bohr to explain hydrogen. And then what happens is that for large enough potential difference between the anode and the cathode, the gas inside would suffer kind of a breakdown, right? Not mental breakdown, but the positive and the negative charge would separate, and there would be an electrical flow, through the gas. And that means that, there's electrons flowing in the opposite direction, right? Electrons are flowing in this direction. And electrons would hit the atoms, and the atoms would go into some excited state. And then they would spontaneously jump down to their lowest energy state. And in this process, of course, a lot of it was understood later. In this process, what will happen is that, this gas would emit photons. And you could see this photon, and you send this photon through a spectrometer, and you could measure their frequency. Now, according to classical electrodynamics, the frequency distribution of the electron should be continuous. Of the photon. Sorry. But what was observed in the spectroscope was not something that was continuous. What was seen was that if you plot the intensity of the beams as a function of the frequency, it was seen that there were these discrete lines, and these discrete lines they came in bunches, and a lot of times they have this sort of asymptotic kind of pattern where the intensity, like there would be a bunching of some of the frequencies at one end, right? And this is not something that comes out of.
Was this the one that concluded that they have discrete energy levels?
Exactly. Yeah. So these series, they had different names depending on who discovered it. I think, like names like the Bomber series, I think Passion, and I forget the names, but experimentalists had found these series, and the Bohr model was able to explain this spectrum extremely successfully, and that was like a spectacular success of the Bohr model. Okay. So, and yes, of course, the Bohr model was it was something that was consistent with the Rutherford model. So yes, so in that sense, it was also a confirmation of Rutherford's experimental evidence that the atom was mostly empty space with a very dense nucleus. All right, so let's discuss the ad hoc assumptions that Bohr made. So the idea came from spectroscopy, okay? Have any of you actually worked with a spectroscope?
I don't think so. No.
Rahul or Wajiha, you guys have done some
Not really.
lab,
The
right,
ones in the Brachio lab are broken.
You haven't worked with a spectroscope. This was the joy of my life. This is what got me into physics, the darkroom spectroscopy. Before that, I was not very serious about physics, but my second year undergraduate lab, where we did all these experiments and analyzed all different gases and their spectrum, was just like, oh my God, it was just so much fun. I would just forget time, and I would just like spend so much time in the dark room doing experiments. Oh my God. Anyway, it was hopefully at some point Bragg will have the space and the resources for a decent physics lab. In the meantime, yeah, you can hear about it. So what are the ad hoc assumptions? So one was that the angular momentum or angular momenta, of the electron orbits, around the proton or the nucleus was quantized, okay? And this was inspired by, a kind of rule of thumb, principle, known as the Wilson-Sommerfeld quantization rule. And what Wilson and Sommerfeld said was that suppose you have a classical system, okay, and you want to find some sort of quantum version of it, then what you do is that we know that for classical system, we have something called a phase space, right? Where you have some axes, which are the generalized coordinates, and you have some axes, which are the momentum, generalized momentum. And according to classical mechanics, the evolution of the system is given by a particle, moving through this phase space. So this is a phase space. And the motion of the particle through the phase space is determined by an energy function called the Hamiltonian, and it's a function of P and Q. And what Wilson and Sommerfeld said was that, we can't, quantize the arbitrary classical system, but they came up with a rule to quantize periodic classical system. And the idea was that, periodic classical system essentially will have some kind of, closed orbits, right? It doesn't have to be, it doesn't have to be a circle. It just has to be a closed orbit. Now, what Wilson and Sommerfeld noticed is that if you take, P and you integrate the P over this closed loop, then it will be given by 2 pi h. Okay. So because so what they're saying is that the area of, because this is going to be the area, right? And this is going to be the area enclosed by this loop. So what Wilson and Sommerfeld were saying is, 2 pi n of h. There's an integer, okay? And what they were saying is that, area in phase space is quantized, okay? And Bohr's first assumption that angular momentum of the electron around the proton is quantized is essentially a restatement of that. Let me just the cat wants to come in, so let me open the door. Schrodinger's kitten wants to join quantum mechanics class. How wonderful. All right, so that was ad hoc assumption number 1. And the ad hoc assumption number 2 was that the orbits of the electrons around the nucleus were, I should say, non-radiating. Okay. So that's also an ad hoc assumption, okay? So as I said, despite these limitations, the Bohr model was a huge success. And people realized that there was something about quantum mechanics that must be true.